Thank you very much for the introduction. So yeah, today I'll be talking about a project that we're involved with a few industrial partners to develop a sensor that allows us to make inoperative measurements of the tissue stiffness to detect cancer. So the motivation behind the project is that the tissue stiffness of the tissue, the stiffness of the tissue is a good marker for locating where the cancer is in the body, as cancer tissue is known to be stiffer than the healthy tissue around it. So when the surgeon is doing their operations, they will make their decisions on the surgical margin and how much tissue to remove based on just sort of feeling around and seeing where the stiff points are. However, with the sort of introduction and increasing growth with robotic surgery, the surgeon's completely separate from the patient. And so they've lost that tactile feedback that they normally have during the surgery. So the aim for this project is to develop a sensor that can integrate with robotic surgery and robotic tools to measure that stiffness as the surgery goes on. So brief sort of outline of mechanical testing that can be done on the tissue. So typically it's done sort of indentation based. So on the left we have indenter here, some tissue sample at the bottom. And as we would indent into that tissue, so indentation up, we'd measure the force response from that. And for stiffer cancerous tissue, then that force will go to higher read points compared to the healthy tissue. If we were to hold that indentation at this depth, then you'll see the tissue sort of relaxing and reduction in force, which again can be linked to the healthy or cancerous cell. And then retracting back, you get another sort of part of the curve. And these can be used to identify the stiffness of the tissue that was in question. What I'll be sort of showing today is mainly on the indentation part, rather than the other methods, but in the future we can look at those. So brings us to what the sensor actually looks like. So we've got this sensor here, which is designed around 15mm diameter, which was chosen as that's the size of the surgical port that is used to allow the tools to enter into the body during the surgery. And this is a cross-section of how this looks. So we have two ports for inlet of fluid, which has a pump attached, so we can change the pressure within this part and create an inflation on a flexible membrane to get a sort of protrusion into the tissue that's in question. And we also have a fibre optic sensor. So we have a fibre optic that's placed through this channel, which is measuring the gap between here and the tip of the flexible membrane. So as the indentation occurs, this depth will decrease and the pressure within the system will increase. Now the way this fibre gap sensor works is we've got a fibre and a reflective membrane. And you get reflection back and forth from each surface, which creates an interference effect. And looking at the spectrum, you get this oscillation of bright and dark zones as you go along. Now this the frequency of this oscillation is directly related to the gap between the two reflections. So if you take Fourier transform of this, you get a single spike at the length that's associated with that cavity. If we were to increase that get distance to be higher, then you get more fringes appearing, and your Fourier transform spike moves further away. So we can use that to get a good accurate measurement of the cavity length in the sensor. To outline how the sensor system all goes together, so we've got a light source that comes out through a fibre into a circulator, which sends it out through this port here towards the sensor. You get these reflections happen here. This reflected light comes back along and into a spectrometer, which allows us to look at the spectrum of the response. That's triggered by an Arduino measurement system, or Arduino microcontroller, which is also taking a measurement of the pressure from a fibre pressure gauge. That allows us to synchronize the pressure and the spectrums or cavity length to the exact time. So this pressure gauge is also a fibre optic pressure gauge, which allows us to insert a pressure gauge and get a measurement very close to where the sensor is actually pulled, so that we don't have to account for any sort of lag or sort of decay within the system. Again, we've got a pump to sort of increase the volume within the cavity to create different indentation depths. And all this is controlled by a computer. So this brings us to how we've actually done the tests that we've presented today. So we've got the sensor here. We pre-inflate it to a particular depth and given pressure. And then we move the whole thing on a mechanical stage into the sample. And that stiffness of the sample will introduce a sort of back pressure and compress this membrane back down, so the gap here will decrease and the pressure will rise, as illustrated on this figure. So to do these tests, we start with silicon phantoms, which are used as a tissue mimicking medium, which we can control the stiffness of by controlling the amount of deadener, as it's called, into the mixture. So the higher percentage of the deadener we use, the softer the material becomes. So to sort of test that the sensor will work the way we want it to, we created 3 different samples per each percentage that we've mixed, and we've got a range of mixtures from 0 to 6% of this deadener. And that's the sort of dimensions that we're dealing with. So to test that these were given a response that we'd expect, we used a commercial indentation system, which just indents by a fixed distance and measures the force on the load cell. And we can see that the stiffest, or lowest deadener percent, which would be the stiffest phantom, records the highest force response, and that decays down based on the stiffness. It's not necessarily a one-to-one or linear relationship between them, but the trend is there, which is as expected. So that gives us a range of what we can expect and relate to human tissue. So then, going from there, we move to testing the same phantoms with our sensor. It's similar trend. We get slightly different response based on the fact that we've got a flexible membrane rather than rigid indenter. But generally, everything holds trend-wise. But going from there to get to that forced indentation curve, we have to relate it to some non-linear hypoplastic model, which the VO model, which basically gives us what stress the tissue is undergoing for a given extension ratio or strain, for simplicity. And this gives us 3 different coefficients, C1, C2, and C3, which based on varying the deadener percentage or stiffness. So as we get to softer samples, the coefficients vary in different ways. To make use of this, we apply a fit. We use just a linear fit for these and our parabolic fit for these 2, just to give us an idea between going from the fitted coefficient to a percentage of deadener or stiffness. This allows us to not necessarily rely too much on the absolute value of the stiffness as such, because what we're mainly interested with the measurements is the contrast between where the stiffness, the cancerous nodules will be, and the healthy tissue. What the reasoning behind this is for patient-to-patient variation, that can be as large as the same patient's contrast between healthy and stiff. So one patient's cancerous tissue might be as soft as another patient's healthy tissue. So we're just mainly based on contrast. So to verify this, we created 3 different phantoms, again just using silicon, but we picked 2 different deadener percentages, soft 50% to represent the healthy tissue around it, and 20% to make these spherical nodules that would be embedded inside. These would made with two different diameters. So we've got large 20mm diameter ones and two small 10mm ones, and embedded at two different depths, 15mm deep and 5mm deep. And just try and see if we can determine the location and where these nodules would be. So we have the measurements from that. And so the sensor itself takes a single point measurement, and we raster that around and make a grid. Here we looked at 25mm by 25mm and 2.5mm steps. So we've got an 11 by 11 grid. And each point we've worked out what the equivalent stiffness would be. So we can see quite obviously on this 20mm shallow one, so when it's the closest to the surface, we can resolve quite clearly a nodule on the surface, a nodule. However, with the 20mm deep and 10mm deep, with the particular size of phantoms that we used in this test, it's quite difficult to resolve where these nodules are, and they fact they give quite a similar response, which highlights one of the issues with this test, or what this sort of problem space is, that these two can give quite a similar response. So as part of this work, we are also working with some tissue mechanics groups who will be doing finite element modeling to sort of unwrap this problem. So going forward, we will be expanding on this test and making larger phantoms, so we can get a larger area that we're scanning across, and then in future move into extra tissue. So as a summary for this work, we have been developing a fibre optic based palpation sensor, which is designed for use within robotic surgery to measure the tissue stiffness, and test is completed to show the sensitivity on different stiffnesses of phantoms, and we're able to detect a stiff nodule within a soft phantom. And future work is to expand upon this much more. But as acknowledged, we'd like to thank our industrial partners, IntelliPalp DX, CMR Surgical, and the National Health Service in Scotland, and UKRI for funding the research. Open for questions.
Okay, thank you. This paper